All right, let's start again here. So I was just talking about an exterior differential system. A manifold consists of a differential ideal, which is like a set of differential forms which forms a subspace, and it's closed under wedge products. If I take the wedge product of two things in the differential ideal, it's again in the differential ideal. But in addition, well, that's not what makes it differential ideal, in the sense that if I take the exterior derivative of something in the ideal, then it has to again be back in the ideal again. All right, so closed under wedge products and the exterior derivative. An exterior differential system, though, is two things: is differential ideal and also a n form. I'm talking about an exterior differential system on an n-dimensional manifold sigma, of course. And so this is the deal. This is actually exterior differential system with independence condition. You can also talk about exterior differential systems without independent conditions. Not that I'm any expert. I read the book. Carton for Beginners, section 1.9. I'm talking about. Anyways, so definition: an integral manifold of this exterior differential system is well, again, this is exterior differential system we should think of as a pair. At the moment, it's the differential ideal, which defines the equations, kind of in some sense, and but it's a little bit more than that. It's the equation, but it's also our notion of contact structure as we actually implement it on jet space or something. Anyway, so an integral manifold of an exterior differential system, or a solution, if you will, of the exterior differential system, is an immersed n-fold, which pulls back to zero everything in the ideal and pulls back the independence condition to not be zero. So this generalizes the notion of solution to a differential equation, and this exterior differential system generalizes the notion of a differential equation itself. The exterior differential system is the abstraction of a differential equation. All right, integral manifold is the abstraction of a solution to a differential equation. All right, you can even talk about these so-called integral elements of the exterior differential system, potential tangent planes, but I'm not going to get into that. That doesn't have too much impact on us here. The next thing to talk about, all right, is the notion of k-jet equivalence. So basically, if I have a function f and a function g, and their mappings from R to R, with the following conditions, so like f of 0 equal to g of 0, all right, equal to 0, and we also have f prime of 0 equal to g prime of 0, and so forth and so on, all the way out into the kth derivative. Oops, I wrote the g first, oh well. Then if you have all these conditions, basically the value of the function and the first k derivatives match up for these two functions, then these are part of the same k-jet at 0. So then f and g are k-jet equivalent. You could look at the set of all possible functions which have these conditions, and you can prove that it forms an equivalence class. I mean, there's an equivalence relation, rather. Then you could look at the set of things, and you partition functions, set of functions from R to R. Let's say smooth functions, just to keep it simple. You can partition the set of smooth functions into these k-jet equivalence classes. And you talk about two functions defining the same k-jet if they have the same initial derivative data up to kth order. Okay, so then that's preliminary definition. Then what we're really after is the notion of a k-jet of manifold maps. So if we have f and g mappings from m to n, such that, let's say, 1 f of p equals to g of p equals to q, and 2, if you have mapping, say, u from the reals to the manifold m, and v from the manifold n to the reals, such that u of 0 is p, then if v composed with f composed with u and V composed with G composed with U have the same k-jet. In other words, if they're k-jet equivalent. If you have these two conditions, then F is k-jet equivalent to G, right? And that basically, folks, is what we need. I mean, so you look at the sets of k-jet equivalence classes, and this is how we build the jet space. Or this is like a cool way to build it anyway. So just to get to the point, the kth jet space of maps from n to n, all right, is the set of k-jet equivalence classes. Now, Rentland actually has a construction of the tangent space in this way. I didn't talk about it in class, but you can also define the tangent space in terms of like quotient, something like this. There's a section in Rentland that I did not cover very well, or if at all. Okay, anyway, getting to the point, the question then is, what are the coordinates on this? It actually is a finite dimensional manifold. This jet, the kth jet space of maps from m to n, and here's how it works. Here's the coordinates. Really what I'm trying to get at to at least help you do my silly homework problems. So if m has coordinates x upper I, and if n has coordinates, let's say u upper A, then the kth jet space from m to n has typical coordinate system like this. It goes xi, and then ua, and then you have the first jet coordinates, like p upper A lower I, and then the second jet coordinates. I mean, these are the new coordinates, new to the second jet space that weren't in the first one. So it's say uij, p upper A. There's always only one upper index, and then you keep going, and you get p, I1, I2, ik. Now these indices, for our bookkeeping convenience, we could think of these as being increasing, strictly increasing. Well, not strictly increasing, rather, just increasing. And here, of course, I equals, let's say, 1 to, oh, I don't know the counting, dimension of m anyway. And here A is equal to 1 to dimension of n, of course. Now, this jet space, basically what it is just, it's the home of your independent variables, your dependent variables, and then all their derivatives up to kth order. That's all you really want here. So just as an example, since I got to run and give a Calc 3 final, I'll try to say more about this in some later video. But so for example, if I was looking at the kth, well, let's keep it simple. Let's say the second jet space from R2 to R, this would have coordinates like, let's say x, fine, I'll keep with the numbering, x1, x2, and then you got yourself p. Now there's just one, so I mean this index is kind of stupid, but I'll write it. P11, P12, P111, P112, P122. So these are basically modeling first derivatives. These are going to be used to model second derivatives. We'll talk about the notion of lifting a mapping up to the jet space in terms of these jet coordinates. These extra jet coordinates are going to be built from the derivatives of the function on the base space. And then conversely, you can talk about which surfaces inside the jet space correspond to actual lifts of functions on the base space. And then we'll look at a specific algebraic condition in the jet space which encodes the differential equation. And then we also need to generalize the theta to several variables so we can make contact between the dependent and independent variables as to impose the derivatives on the higher jet coordinates. It's all very beautiful and interesting. And it does tie into this notion of the Frobenius theorem. And that's the part I'm, again, struggling to make more explicit. There are actually some great PDFs which are sort of expositions. Other people trying to grapple with understanding Cartan for beginners. I'll send you a link to a couple of them if you're interested. And there's also kind of great calculations about, you know, the tangent vector fields to these integral manifold solutions, right? There's that too. Anyway, there's so much to learn here. I think it's really, really interesting. But this is, of course, not enough to really understand. I'm just getting started. Oh, I got to give a test. So, thanks, guys.